Alright, I didn't receive any questions in advance, so I've got the chat open. I do need to respond to a few emails, but I am here if you got any questions. Yeah, that's really annoying. Oh well. Oh, actually, a real question. Cool. One question English. Orgo 1, PowerPoint 4. It is about the placement of radical in a compound. I'm confused about knowing when a radical goes to the most substitute carbon, like dealing with HBr radical versus in a thermodynamic product. When it goes into a carbon that has better resonance, that is not the most substituted carbon. So, sorry if this is confusing. I've been looking at slides 30, 31, 83, 83, and 86 through 88. So let me bring those slides up. Hopefully I've already got them on the desktop. Let's see. All snap halides. Nope. Okay. Let's download them from the course website. Ah, score. Got a jury duty. Sorry. I am looking this up. I just got to wait for it to download. I was supposed to report to jury duty next week, so I was really hoping I could get out of it. It's like, man, y'all could not have picked a worse time to send me to jury duty. All right, it's almost done opening. All right, so 31 is talking about this mechanism. So we have initial attack. So we generate the free radical. And we get attack of the molecule to give us this, which is why we get the anti-Markov-Nikov product, because we form a more stable radical on the tertiary. I got the letter 2 weeks ago, and of course they're doing everything through the mails. Like, why are you going to the United States Postal Service right now for this? This is really important. But I've generally found the jury duty, they're pretty responsive. Like, if you say, hey, I've got this going on. Okay. So slides 80 through 83 talk about how you can draw the same analogy with carbocations as you can with free radicals. So this is also true that if you end up having a molecule radical, you actually end up with a lot of different resonance structures, particularly for something like this conjugated polyene. And questions slides 86 through 88. And the reality is that you can end up, so it also comments that particularly with what are called allylic carbons, so allylic carbons are those that are adjacent to double bonds, we can end up getting substitutions around those allylic carbons. Okay, I see where the confusion is. So you're actually looking at two different reactions, so that's confusion. So let's say we have two reactions. So we have HBr plus light, which will give us, or we have peroxide, something to generate radicals, and then we have something like Br2 light. So in this case, this is an addition reaction. And this is a substitution. So with the addition reaction, here, we'll put a tertiary on here. This is where we're going to do the anti-Markovnikov. So the addition here is going to be across the double bond, and we're going to end up producing this compound here. For substitution, the substitutions are actually going to take place on the allylic carbons, and they're going to take place on the allylic carbons because we are going to initially generate a free radical that's going to extract the hydrogen. So in this case, we already have a hydrogen from the HBr, and this is why we're going to get addition. But in this case, we're generating two bromine radicals, and one is going to peel off a hydrogen to give us HBr and a radical, and this radical on the molecule is going to be stabilized by resonance. So this is why we're not going to get Br addition across the double bond, is because we initially generate a radical by extracting a hydrogen from this molecule. Now for addition, we've already got the hydrogen radical in place. So I know it's kind of like a hand-wavy explanation. I'm not explaining it the best, but I think the confusion here is that you're trying to equate addition and substitution. For addition reactions, this is where you get the anti-Markovnikov, and it's going to add across the double bond. For substitution reactions where you see this Br2 light, we're not going to end up not getting addition across the double bond. We're going to end up getting free radicals that are generated by extracting a hydrogen from the molecule. Now, if you're also picking up on this vibe, is like, well, why would the bromine radical here start attacking these in the same way? Like, why does the molecule know the difference between a Br2 radical and an HBr radical? This is the dirty truth of halogenation. It is sloppy and it is dirty, and this is why nobody really does halogenation reactions with free radicals. So we teach you free radicals because historically this is what's been taught. It's a nice kind of primer on how to work with substitution reactions. But anything like HBr and Br2, once you start introducing free radicals, this is a nice idealization of the molecule to say, oh, it will cleanly substitute onto all the different carbons like it's supposed to. The reality is you would probably have the addition product like there isn't any light, so you would get the bromine attaching to the double bond. You would get substitutions all along. There would be a lot of things going on. So particularly when you see anything involving radicals, this final product you're seeing is an idealization. It's probably not the primary product because it's very hard. It's probably the primary product. There's a lot of side products in there. So hopefully that kind of clarifies it for you. We're going to focus on the radical going to the most stable carbon when we're doing addition reactions. And this is why we get the anti-Markovnikov product. And when we do substitution reactions, not addition product reactions, so we're still remaining with the alkene, this is where we're going to get the most stabilized free radical. Yeah, you're welcome. Yeah, I've talked to a lot of people, and like no one does free radical unless they have to. Oh, ooh. Looking at the figure on page 9 too. Oh, okay. I didn't actually give you that problem. That's just a picture. Yeah, good question. explain on how beta carbons can figure out how many products will be created via elimination. So let's take a look at what I got asked earlier. So the example that was given with this, I don't like the example the homework gives. Really, you would rather run this with a big base like terp-butoxide. So in this case, we only have one choice. So we're eliminating the alcohol, and we need something with a beta hydrogen. So we've got 3 beta carbons here. This has a hydrogen, this has a hydrogen, this doesn't. So really, we've only got one product. And the reason we only have one product is that, one, this is an achiral center, so there's no way to generate a cis or a cis transversion from the alkene. And on top of that, there's really no way to eliminate from this carbon because there's no hydrogen. But let's say we change the molecule to look like this. So we still got our terp-butoxide. That drew that weird. So how many different products can we have? Well, we have 3 beta carbons we can go off. So let's just write the product. So the first one will eliminate between these two. We'll eliminate between these two. And we can eliminate with this one, but let's keep in mind that when we draw it, there's 2 ways to draw it. So here we've got the cis form, and here we got the trans form. So here we got 4 potential products based off of the fact that we've got 3 different beta carbons, and then we've got a beta carbon that can rotate so we can get both the cis and the trans conformation. So there's a little bit of trial and error with this. The big thing is, one, keeping track of your mechanism. So in this case, you work with terp-butoxide. This assures that we'll get an E2 mechanism. If we go to an E1 mechanism, ooh, how can this mess us up? Okay, with this one, it doesn't matter. But if we had a situation where this could rearrange, that's another thing that can generate more products. So first, identify your reaction mechanism, E1, E2. If you end up with an E2, you don't get carbocation rearrangement. So you're always eliminating from this carbon. If you have E1, which is a polar protic solvent, typically alcohol dehydration using sulfuric acid, H2SO4, you can also, not only do you have to look at what you'd expect for the E2 products, you'd also have to look at what you'd expect for carbocation rearrangement if it does occur. So for this one, let's say we switch to this molecule, and we did it with sulfuric acid. We've got 2 beta carbons. So we can eliminate from here to here, here to here. So if we did this by an E2 mechanism, we can get this product as well as this product. So we can get the trans and the cis version. If we get carbocation rearrangement, our carbocation can relocate by hydride shift. So by the E1 mechanism, we've got a carbocation, we can rearrange that to give this carbocation. Now I'm back in the same scenario. I've got 3 beta carbons. 2 of them look the same, so this is a potential product. And then we can eliminate from here to here. Sorry, I know I'm running out of space. Let me see what you can see on the camera. Yeah, got a little bit of space beneath it. I can also create this molecule as well. So there are 1, 2, 3, 4, 5 potential products. Based off of the reaction conditions, from there you can figure out what's most likely to happen. So with Zaitsev's rule, we eliminate from the most substituted carbon. So this is probably, not that one. That one's probably not going to happen. Also by Zaitsev's rule, oops, sorry, I forgot one of the E2 mechanisms. Six products, 1, 2, 3, 4, 5, 6. By Zaitsev's rule, we're probably not going to create these 2 as well, so this is probably going to be the predominant product. And then if you go by the E1 mechanism, you're probably most likely going to create this product. So in terms of like how do you figure it out? Again, kind of back up what you think the mechanism is. Is it E1 or E2? If it's E2, it's a lot simpler. You just start drawing out to the different beta carbons, and you're probably most likely going to eliminate from the most substituted one that has a hydrogen. If it doesn't have hydrogen, it can't eliminate. If you're going through an E1 mechanism, treat like it's an E2, see what all the products probably are, and then treat like an E1 and do some carbocation rearrangement if it's possible, and see what products you get from there. And again, Zaitsev rule is going to dominate. You're probably don't need to draw all the possible possibilities. You probably need to draw the one that eliminates off the most substituted carbon, beta carbon containing a hydrogen. But be aware that in reality, you're probably getting a mixture of all these, with the Zaitsev rule product being the favored one. I hope that kind of explained it. I don't know. I feel like I kind of like wandered off there. Yeah, you're welcome. For the discussion board, the second part of the question, do we skip steps 1 and 3 to find the possible products? So let me bring up the discussion board. Yes. So you only concern yourself with products 2 and 4. So product 2 is going to be this one, and product 4 is going to be your diol or diene. So the chloromethylcyclohexane and the trans dichloromethylcyclohexane, those are just intermediates. They're meant, number 1 and number 3 are meant to be review from test 2 and test 3 respectively, just to make sure you're not forgetting those reactions. Same thing about, yeah. And 2 is also kind of a review from the last test material. This is the new material, which is the Diels-Alder product. And Diels-Alder is probably the hardest thing you're going to work with. I try not to keep this. What you're seeing here is a pretty hard case on the discussion board of Diels-Alder, just because it's hard to keep track of everything. The Diels-Alder, though, is a good example of like why you need to be judicious in selecting reagents, because there are a lot of products you can form by Diels-Alder. And I actually had a lab discussion board, because it's something I had to work with, where it talked about you run the Diels-Alder product and then suddenly you get like this massive wax at the bottom of your reactor. What's the massive wax? The Diels-Alder product can sometimes react with itself because you always finish up with that double bonded carbon. So your diene can attack the double bond on the product and so forth. And so unless you keep these things sufficiently dilute, you'll end up kind of like creating this polymer when you're done. But that's practical stuff. Hey, you're very welcome. Questions 54 and 59 on the 251 homework. All right, let's bring that up. So question 54, give the structural formula of the carbocation intermediate that leads to the major product in the reaction of hydrogen chloride with cis-2-butene. So reaction intermediate here, we're going to have nucleophilic attack with a double bond onto the hydrogen, and this will give us this carbocation. So I'll switch to the desktop so you can see it. And I realize right now I just drew transbutene. It's not going to change the answer. So that's it. And then question 59. Draw a synthesis of 2-ethoxymethylpropane from 2-methoxypropene. And like always, it's really obnoxious the arrow points the wrong way. So we're starting out with this alkene and we want to make this compound here. So I'm looking at the intermediates. So look at a precursor to the starting molecule. So I got a few ways I would do this. I would just open up the epoxide ring. Well, okay. So it gives you the following options. Oops. So I can think of two ways you could synthesize this molecule. With either A or D. So this can't work. There's no way you can directly jump from this to the ether that's being produced. This you'd end up having to break the carbon-oxygen bond. This really isn't a particularly efficient way, and this one requires a lot more functionality. So it's going to be one of the two, A or D, in this problem. So let me see if there's any context here. So the way I could do it from A is do a nucleophilic attack on the tertiary carbon and break open that epoxide. Well, actually no, I don't like A anymore. So if I had the epoxide and I did a nucleophilic attack of F oxide, it would open that up, but now I'm going to end up with an alcohol when I get done. So that won't work. But if I do an ethoxide attack on this, in principle, I can displace the bromine. So my gut instinct here is to say that I'm probably going with this this compound. Yeah, appears to work. All right, so to make the alkyl bromide really easy, you're just going to take this this 2-methylpropane and you're just going to react it with light and bromine gas to give you this substituted product. Wait, what? It is an efficient way. Okay, option A is option A is that you can just take that and add HBr to it. Okay, fair enough. They're probably right. After I just got done titrating that free radical elimination is not the best way to do it. So next part, check the precursors. So in terms of converting this double bond, this 2-methyl 1-propene to the 2-methyl 2-bromo compound. Easiest way is just do it with HBr because you do want the Markovnikov product. And then the best way to react this is that if you just work with the eth oxide. Come on, I know you're in here somewhere. B. The eth oxide will undergo nucleophile attack on the bromine. What? Try a less basic reagent. We can try hydrolysis. Yeah, okay. So apparently it's saying it will do elimination. I don't think ethoxide would do the elimination, but you could also use solvolysis, which is as well. All right, so to recap. We want to make this compound starting with this compound. And we're going to do it in a couple of steps. So the precursor way we're going to go back from this is to start with the 2-bromo 2-methylpropane. And we're going to convert this to this by using HBr. Pretty straightforward step. Because the HBr bromine is going to end up on the most substituted carbon, this is a pretty straightforward reaction to run. You would probably just run it at room temperature. To convert this to this, I personally would use eth oxide, but you can use a technique that's called solvolysis. They're probably right. I grant them on that. The issue with using something like eth oxide, you can get some elimination, particularly if the eth oxide opts to pick off of that carbon versus doing a substitution. That said, what they're claiming, and I can see their argument, is that the ethanol will attack the bromine to knock it off. So you'll end up with this intermediate, and then the bromine is going to extract the hydrogen back off to give you that product. And it's funny because I propose the epoxide and completely forget that we don't really cover epoxides that heavily in organic 1. That's why a little knowledge is actually a good thing in this course. The less you know, the less stuff you have to complicate it. That's right, it's organic 1, and y'all haven't really done epoxides that much. Yeah, you're welcome. All right, looks like 0 concurrent viewers going on right now. So again, with any live stream, please feel free to email me any questions in advance. Discussion boards are always open. So I will see some of you tomorrow.